Welcome to the playlist of videos on essential statistics for data science. I am Hemakumar Kasala, and in this video I will explain you in detail on the following two fundamental distributions, namely normal distribution and standard normal distribution. By the end of the session, you will thoroughly understand what is a normal distribution, what is a standard normal distribution, in other words a Z-curve, how are probabilities evaluated for a standard normal distribution? How are probabilities evaluated for a normal distribution using a standard normal distribution? How to judge if a sample data is normally distributed? What is normal probability plot? How to transform data into a normal distribution when the sample is not normally distributed? And how to arrive at probabilities for a discrete probability distribution using normal approximations. Let's get into the video. Normal distributions are widely popular continuous probability distributions. The reasons are they provide reasonable approximations to the probability distributions of many different random variables, and they play an important role in the inferential stages in statistical experiments. Normal distribution is a bell-shaped curve centered around the mean mu and with a standard deviation sigma that quantifies its spread around the center. Since the area under the normal curve equals 1, the normal distribution is narrower and taller when sigma is small and wider and shorter when sigma is large. From a maximum value above mu, the normal distribution curve, also called as normal curve, starts falling with constantly increasing downward slope on either side. Reaches the maximum downward slope at mu plus sigma and mu minus sigma, and thereafter the slope starts reducing and reaches a near zero value as the curve approaches the variable axis. The primary motivation behind approximating a probability distribution using a normal distribution is to arrive at various probabilities associated with the random variable x. What is the probability that a newly born infant weighs more than 8 kgs in a given childbirth hospital is the question for which the normal distribution approximation help provide the answer. The shaded area under the normal curve to the right of the value 8 on the x-axis, probability of x greater than 8, is the answer to the above question. And similarly, area under the normal curve between 6.5 and 8 provide the probability that a child born in that hospital weighs anywhere between 6.5 and 8 kgs. That is, probability of x greater than 6.5 and less than 8. However, computation of the above listed probabilities for any normal distribution with a certain mu and a sigma is not straightforward. To make the computations easy, a reference normal distribution is resorted to, for which a comprehensive list of probabilities are already calculated and made available in a table form. That reference normal distribution is the standard normal distribution. Standard normal distribution is a normal distribution whose mean value mu equals 0 and the standard deviation sigma equals 1. Also called as standard normal curve, the area under the curve equals 1, like in case of any probability density distribution including the normal distribution. The variable is denoted as z, and hence the curve is also called as the z-curve. The kind of probabilities that are often evaluated on a standard normal distribution are: what's the probability that z takes a value less than c? What's the probability that z takes a value greater than c? What's the probability that z takes a value greater than a but less than b? And what are the z values minus z star and plus z star that divide the extreme 5% of z values. While the first three cases aim at arriving at the probability values associated with a z value or a range of z values, the last case aims at arriving at the z values given the probability value. Let's understand how we go about evaluating these probabilities and the z values one by one. For a standard normal distribution, these probabilities are not usually calculated using analytical formulas. Instead, derived from tables called as z-tables. The first column and the first row constitute the z-values, and the contents of the table provide the probabilities. Table on the left is meant to evaluate probabilities associated with negative z-values, and the table on the right is meant to evaluate probabilities associated with positive z-values. For example, probability that z takes a value less than or equal to minus 1.94, where minus 1.94 equals minus 1.9 plus minus 0.04 equals 0.0262, that is 2.62%. Similarly, probability that z takes a value less than plus 2.53, where 2.53 equals 2.5 plus 0.03 equals 0.9943, that is 99.43%. In general, the table provides the cumulative probability for a z value not exceeding a selected value a. In other words, probability of z less than or equal to a. For example, if a equals 1.16, the cumulative probability of z less than or equal to 1.16 equals 0.8749. In other words, 87.49%. To find the probability that z takes a value less than or equal to c, map the value of c such that c equals a plus b, where a equals the integer and the first decimal part of c, and b equals the second decimal part of c. Approximate it to second digit where c extends beyond 2 decimal digits. Probability of z less than or equal to c equals the value in the table whose position is identified by the row corresponding to A and the column corresponding to B. Let's now evaluate the probability of z taking a value greater than c. Probability of z taking a value greater than c equals 1, which is nothing but the entire area under the standard normal distribution curve, minus probability of z taking a value less than or equal to c. Pick the value from the z table for probability of z taking a value less than or equal to c as discussed, and subtract it from 1. Thus, probability of z taking a value greater than c equals 1 minus probability of z taking a value less than or equal to c. Similarly, probability of z taking a value between a and b equals probability of z taking a value less than b minus probability of z taking a value less than a. Pick the values from z table for probability of z less than a and probability of z less than b, and subtract probability of z less than a from probability of z less than b. Coming to the last case where we derive z values when a probability value is specified. What are the z values minus z star and z star that divide the extreme x% of the observations? Since extreme values are symmetrically distributed at either ends, the x star gets equally divided as x by 2 at both ends. We are interested in finding the value for z star for which probability of z less than or equal to z star equals 1 minus x divided by 2. Let's first locate probability of z less than or equal to z star in the z table. For example, if x equals 5%, the probability of z less than or equal to z star from the z table is 1 minus 0.05 divided by 2, which equals 0.9750. Z value corresponding to 0.9750 is 1.96 in this case. Since the z value that divides the top x by 2% of the values is 1.96, and because of symmetry, the z value that divides the bottom x by 2% of values will be minus 1.96. Therefore, the z values that divide the extreme x%, that is 5% in this case, of values are minus 1.96 and plus 1.96. Having understood the standard normal distribution, the z-curve, and how to derive various probabilities from the z-table, let's proceed to learn how to derive various probabilities for other normal distributions whose mean value does not equal 0 and standard deviation does not equal 1 by using the standard normal distribution. In order to do that, we need to understand the relationship, in other words, the mapping between the two distributions. Let's consider a normal distribution for a random variable x with mean equals mu and standard deviation equals sigma. Let's consider two arbitrary values a and b in x. Suppose we subtract mu from x and plot the normal distribution for x minus mu. We have this. Mean equals x minus mu, which equals mu minus mu, which is 0, and standard deviation remain unchanged at sigma. Value a translates to a minus mu and b translates to b minus mu. Literally, the normal distribution for x minus mu shifts by mu towards 0 on the random variable axis. The distribution as such remains the same, but centered around 0 instead of mu. Now we divide the normal distribution for x minus mu by sigma and plot the resulting distribution. We have this. Mean remains unchanged at 0 and standard deviation equals sigma divided by sigma, which equals 1, and value a minus mu translates to a minus mu divided by sigma, and b minus mu translates to b minus mu divided by sigma. What we have arrived at by carrying out these steps is nothing but the standard normal distribution where mu equals 0 and sigma equals 1. Normal distribution of x with mean value mu and standard deviation sigma transforms into a standard normal distribution when mu is subtracted from x and resultant is divided by sigma. X minus mu divided by sigma equals the standard normal variable z. Thus, z equals x minus mu divided by sigma. The probabilities associated with a value, for example a in x, is the same as associated with the z value a minus mu divided by sigma on a standard normal distribution. Hence, it is possible to derive the probabilities associated with any value or interval in x by mapping that value or interval in x into a value or interval in z and pick the probability from the z table. Let's explore a few examples. Outcome scores of an IQ exam results in distribution of scores x, which is approximately normal, with a mean value mu equals 100 and standard deviation sigma equals 15. This exam is conducted by a premier institution and the qualifying IQ score for admission is 130. What percentage of aspirants who attended the exam will qualify for admissions? In other words, what is the probability that x takes a value greater than or equal to 130 in order to qualify for admissions. Probability of x taking a value greater than or equal to 130 equals the shaded portion. X equals 130, mu equals 100, and sigma equals 15. Z of x equal x minus mu divided by sigma, that equals 130 minus 100 divided by 15, and hence z of x equals 2.0. Hence, probability of x taking a value greater than or equal to 130 equals probability of zx taking a value greater than or equal to 2.0. Probability of x greater than or equal to 130 equals probability of zx greater than or equal to 2.0. Probability of zx greater than or equal to 2.0 equals 1 minus probability of zx less than 2.0. Probability of zx less than 2.0 equals 0.9772 from the z table. Hence, probability of zx greater than or equal to 2.0 equals 1 minus 0.9772, which equals 0.0228, which is 2.28%. And thus, probability of x greater than or equal to 130 equals probability of zx greater than or equal to 2.0, which is 0.0228, in other words 2.28%. Therefore, 2.28% of the aspirants qualify for admission. Now suppose we want to know the IQ value A that divides the top 1% of IQ scorers from the rest. That is, the value A in probability of x greater than or equal to A, which equals 0.01. Probability of x greater than or equal to A equals probability of z greater than or equal to ZA, which equals 0.01, where ZA is the z value that maps to the value A in x. Probability of z greater than or equal to ZA equals 1 minus probability of z less than ZA, which equals 0.01. Thus, probability of z less than ZA equals 1 minus 0.01, which equals 0.99. Locating the z value corresponding to 0.99 from the z table, we derive ZA as 2.33. ZA equals 2.33 equals A minus mu divided by sigma. Thus A equals 2.33 multiplied by sigma plus mu. Substituting the values for sigma and mu, we have A equals 2.33 multiplied by 15 plus 100, which equals 34.95 plus 100, which approximately equals 135. And thus, the IQ value A that divides the top 1% of IQ scorers from the rest equals 135. We saw two illustrations wherein the standard normal distribution is used in arriving at 1. Probabilities associated with the normal distribution variable x, like in probability of x greater than or equal to A given a value A in x, and 2. Values in normal distribution variable x given their associated probabilities. In order to transform a distribution into a standard normal distribution and evaluate the associated probabilities, one must be sure if the data sample being examined is close to a normal distribution. A sample data distribution that is nowhere close to a normal distribution cannot be mapped to z-curve, and hence the inferences cannot be made as discussed so far. Hence, it is essential to judge if the sample data at least fairly complies to a normal distribution. One such means to verify if the sample data is normally distributed is the normal probability plot. The sample data is plotted using a scatter plot against normal scores in a normal probability plot. The normal probability plot that confines to a straight line confirms that the sample data is close to normally distributed. What are normal scores and how to plot them against the sample data? Normal scores are predefined set of values. Normal scores are available in distinct sets of various sizes. The size of the normal scores set chosen equals the size of the sample data n that one wishes to plot, such that the normal score set and the sample data are equal in sizes. Values in normal score sets are derived from a standard normal distribution. The lowest value in a normal score set of size n equals the long run average of lowest scores from samples of size n extracted from a standard normal distribution. The second lowest value in a normal score set of size n equals the long run average of the second lowest scores from the samples of size n extracted from the standard normal distribution, and so on. The highest value in a normal score set of size n equals the long run average of the highest scores from the samples of size n extracted from the standard normal distribution. Ascendingly ordered sample data of size n is paired with ascendingly ordered normal scores. Each value in the sample data is paired with the value in the normal scores by matching their position in the order, meaning lowest sample data with the lowest normal score, second lowest sample data with the second lowest normal score, and so on. Normal probability plot is a scatter plot plotted using these value pairs. Sample of size n extracted out of standard normal distribution when plotted against normal scores set of same size n shall align on a straight line at 45-degree angle. Sample of size n extracted out of any other normal distribution when plotted against normal score sets of same size n shall approximate to a straight line with a slope that is decided by the sample data. Sample of size n extracted out of non-normal distribution when plotted against normal score sets of same size n shall not result in a scatter plot that can fit a single straight line. These are the three different possible cases while plotting normal probability plots, which can confirm the normality in the sample data distribution. Transformation techniques can be tried on sample data that does not approximate to a normal distribution. Rainfall data for 30 consecutive years in a particular state is tabulated below. Probability distribution of this sample data does not approximate to a normal distribution. However, applying the square root on the rainfall data, it is observed that the probability distribution approximates to a near normal distribution. Some long-tailed sample data distributions, by applying log 10 or log e transformations, can result in near normal distributions. Similarly, many other mathematical functions like reciprocal, cube root, etc. can also be tried on raw sample data in order to arrive at distributions that approximate to normal distributions. Cases where a normal distribution curve can fit a discrete probability distribution, probabilities for the discrete probability distribution can be derived with some approximation from the normal distribution curve that fits it. Given the discrete probability distribution histogram for a discrete random variable x, probability of x equals a equals the area of the rectangle in the histogram centered at a and extends between a minus 1 by 2 and a plus 1 by 2. If the probability distribution histogram for X fits a normal distribution curve approximately, then the area under the normal distribution curve between a minus 1 by 2 and a plus 1 by 2 provides the fairly close approximate value for probability of X equals a. Similarly, probability of X greater than a and less than b approximately equals the area under the normal curve between a minus 1 by 2 and b plus 1 by 2. Evaluating the probabilities like probability of X equals a and probability of X greater than a and less than b by mapping a and b onto the standard normal distribution are already discussed, provided the values for mean mu and standard deviation sigma for the discrete normal distribution are known. That brings us to the end of the session on normal distribution and standard normal distribution. We discussed on all the topics listed below. Please leave your questions and remarks if any, and I shall respond back as soon as possible. Thank you for watching and see you with the next topic soon. Bye until then.